Hi friends, in this video we are going to see GATE 2023 question paper and the answers are solved in the subject operating systems, and this is a part 2 video and it covers 3 questions, and I already have part 1 video and that also covered 3 questions, totally 6 questions that are asked in the year GATE 2023 question paper. So please subscribe and watch the video completely. So this is the question number 1. Which one or more of the following need to be saved on a context switch from one thread of a process to another thread of the same process? The options given are page table base register, stack pointer, program counter and general purpose register. Which of these registers has to be saved when one thread moves to another thread so that it can come back or completely finish the process? So the first option is page table base register. This register holds the base address of the page table for the currently executing thread, and so all the threads will have the same page table, so there is no need to save this page table base register. Next option is stack pointer. Stack pointer. This register points to the top of the stack of the currently executing thread. Here each thread will have its own stack. So the stack pointer has to be saved and restored on the context switch so that it can ensure the new thread uses the correct stack. So the stack pointer has to be saved when a process moves from one thread to next thread. Next, program counter. This register contains the address of the next instruction to be executed by the currently executing thread. So to resume execution of a new thread, to come back, this program counter has to be saved, also loaded into the program counter register. So stack pointer and program counter both should be saved. Next, general purpose register. This register will store the temporary data and other immediate results that are generated during the execution of a thread. Since the state of this register is different for each time, also while executing the thread, there is a need to save this general purpose register. So when a thread of a process context switch from one thread to when one thread of a process switch to another thread, it has to save stack pointer, program counter and general purpose registers so that it can execute the complete process in a correct manner. Okay, so the answers are B, C and D. So next question. Which one or more of the following options guarantee that a computer system will transition from user mode to kernel mode? So this is an important question. Why? Because every year the GATE question will have one question based on this user mode and kernel mode transition. So please concentrate on this topic, user mode to kernel mode transition. Directly or indirectly, the same questions under the same topic, same concept will be asked again and again. So in my previous videos also you will see some nearly 2 to 3 questions with the same concept but differently they are asked. So please clear about this concept. We can easily obtain marks in this concept. So the question asked here is, which of this function call, MLA call, page fault or system call, which of these 4 will enable the computer system to transit from user mode to kernel mode? So when it comes to function call and MLA call, both cannot enable any transition from user mode to kernel mode. Why? Because these both function call and MLA call are completely execute. All these operations of function call and MLA call will be completely execute only inside the user mode. So there is no need of kernel mode and there is no need of transition from user mode to kernel mode. In page fault, a trigger may cause the transition to kernel mode, because a page fault occurs when a program needs to access a page of memory that is not currently in the physical memory. So there is a there is a chance of need of allocating physical memory or swap of pages from physical to physical memory inside or outside the memory. There may be a chances. So there may be a transition. There may be a chance of taking transition from user mode to kernel mode when a page fault occurs. So there is a 50-50 chances in page fault. So we can't leave this answer. We can include page fault will enable guarantee. It's not guarantee. So we also enable the transition from user mode to kernel mode. In system call, yes, system call definitely guarantees the transition from user mode to kernel mode, because system calls are the mechanism by which user level programs can request services from the operating system. So this will definitely enable the transition from user mode to kernel mode. When a user level program executes a system call, the system call will generate an interrupt to occur. This will transfer control to the kernel mode. Then once in kernel mode, the request that is needed, that is generated by the interrupt or that is generated by the system call is performed. Again, the control is moved to user level program. So each system call will generate an interrupt that will that will enable the transition of control from user mode to kernel mode. Once the request is performed on the kernel mode, again the control is moved back to user mode. So the answers are page fault and system call that enables the transition from user mode to kernel mode. Next question number 3, and this is the last question. So consider the two functions increment and decrement are given here. So here 5 threads are each invoking increment. Once the increment function invokes, 5 threads will run, and once decrement function invokes, 3 threads will run, and both share the value of a variable x. The initial value of x is 10. And here this is simple, but the thing is there are two implementations has to be taken of the semaphores. One is binary semaphore and another one is counting semaphore. So binary semaphore is initialized to 1 and counting semaphore is initialized to 2. Let's have the variables v1 and v2 that are the values of x at the end of the execution of all these threads after implementing binary semaphore and counting semaphore. So which one of the following choices corresponds to the minimum possible values of v1, v2? So what are the minimum values of x after binary semaphore and after counting semaphore will be there? So let's calculate. It looks like somehow difficult, but once you calculate from the step by step, it will be easier. Let's do it. See, the process is doing both binary semaphore and counting semaphore. Initial value of binary semaphore is 1 and for counting semaphore is 2. And for x value it is 10. It is x equal to 10. And for increment 5 threads are there, for decrement 3 threads are there. So first let's consider the binary semaphore is happening. In this first it will take increment function. So first thread, during the first thread s equal to 1, x will be incremented to 10 to 11, 10 plus 1 11, and again it will go to second thread it will run the increment function for the next thread t2. At the time it will again it will increases to 12. Likewise 5 times this thread will execute. After executing 5 threads, we will have x equal to 15. Then we move to decrement function, and here decrement will happen. So after 3 times of decrementation, we will have x is equal to 12. So in binary semaphore, the initial the minimum value of x will be 12 only. This is the only value and minimum value, because in this way only the binary semaphore will execute the threads. When coming to counting semaphore, first decrement will be happen. So here first thread will s equal to 2. So x equal to 10 minus 1 9, and again so during the second thread it will become 8, and third thread it will become 7. So After 3 threads, executing 3 threads, x value will be 7. And then it moves to increment function. There it will increment it 5 times for 5 threads. So it will become 13. And once finishes, it again come to decrement function in counting semaphore. So already in counting semaphore we have value as 7 for decrement function. So here the x value will not change. Again this x equal to 7 will be overwrite the 13 which comes from increment function. So again the minimum value the x value becomes 7 only here. So finally what happens, x is equal to 12 and 7. So the answer will be x is equal to 12 and 7 in counting semaphore. In binary semaphore 12, counting semaphore 7. So the minimum value in counting semaphore is 7 and the only and minimum value is in binary semaphore is 12. So answers will be 12 and 7. So these are the minimum values after completing binary semaphore and counting semaphore. So that's all. With this question, all the questions are covered in operating systems for GATE 2023. And hope you understand all the questions. Please subscribe to get all the questions with answers explained in all the topics of computer science for the year GATE 2023 in my future videos. Thank you. Bye.